Good afternoon. Today I am going to talk about remote sensing and GIS application to hydrological modeling. Today mainly I will focus on what is hydrological modeling, what are the different components required to get to estimate the hydrological flow in the river, then how remote sensing and GIS will help us, and finally hydrological modeling. So first of all, what is hydrological modeling? Hydrological modeling is defined as the mathematical representation of hydrological process. In simple term, we can understand like that. Suppose there is a pipe and water is flowing into it. So let us say the velocity of the water is V and the area of the pipe is A. So the flow in the water is Q is equal to V into A. So this is a basically flow model of a pipe flow. Hence, now let us try to understand the hydrological modeling in real world situation. So as I told you, hydrological modeling is the mathematical representation of hydrological process. So what are the hydrological process? The processes are basically it governs the component of hydrological cycle. These are precipitation, which may be rainfall, which may be snowfall, infiltration, which is finally contributing to soil moisture, interception, evapotranspiration, runoff, which includes surface runoff, subsurface runoff, etc. So let us try to understand the entire process in the form of hydrological cycle. What happens first? We can start from the cloud. So there is a cloud. Now, yesterday also I told you, when temperature is very low, there is a condensation of the cloud and finally it will move down to gravity and you will have a rainfall. So the first component of hydrological cycle is the precipitation. Generally in India, precipitation is nothing simply rainfall, except during winter season you will have snowfall and hilly terrain. Nowadays you must be hearing that there is a snowfall in Manali or Simla or maybe in Nainital. So, but all over India, wherever precipitation, it is in the form of rainfall. So first is the rainfall. Then once rainfall occurs, it will first interact with the land cover, which may be a tree, which may be a agriculture crop, which may be a building, anything, any cover. So it will interact with that, it will be intercepted by that. So it will be intercepted by, let us say, canopy. So some water will be stored in canopy. Once it is completed, then immediately you will find there will be it will go down and there will be it will add to the surface. Immediately after that, evaporation will start because of the temperature and vapor and other parameter will start. Also, there will be overland flow. Also, there will be a infiltration in the ground. So infiltration is nothing simply entry of water to the soil surface. However, this entry of the water to the soil surface, it will increase the soil moisture, and also when moisture is huge, it will further move down and it will add to the groundwater. So there will be soil moisture storage or increase of soil moisture. There will be a subsurface flow or interflow. There will be deep percolation. Then there will be a groundwater flow. Now this will further move down and it will add to the river in the form of base flow. Interflow will further move down and it will add to the river system. Finally, it will add to the surface runoff. Then there will be a channel storage, there will be a channel flow. Then finally there will be a surface storage, a reservoir is there or lake is there. Then finally it will move down to the river outlet. Generally in India we have a ocean, for example Ganga, Mahanadi, Godavari, all these rivers are flowing into the Bay of Bengal, while Narmada, Indus, they are flowing in Arabian Sea. Now, after all this process, there will be evapotranspiration from the plant, canopy cover, surface water, open water body, river, ocean. It will go up and finally it will add and form the cloud. And again, cloud is formulated. So what you see here, the total hydrological process will start from the cloud, then there will be a precipitation, there will be interception, there will be surface, evapotranspiration, overland flow, infiltration, soil moisture, interflow, deep percolation, groundwater storage, base flow, return flow to the river, channel storage, channel flow, surface storage in the lake, surface storage in the sea. Finally, it is good evaporation from sea and lake. Finally, there will be a cloud formation, and you will have again cloud. So this is the entire hydrological cycle. In hydrological modeling, what we have to do? We have to see, generally our interest is that how much flow is coming to the river, because it is the river flow which is useful for the benefit for humankind. Suppose I constructed a dam, I should know how much water is coming to the dam every day, so that that water can be utilized for irrigation purpose, hydropower, or maybe some recreation purpose. Not only that, suppose there is a lake, you want to utilize that lake water somewhere, you should know how much water is coming to that. To know that, there is a relationship between rainfall and the runoff. So, runoff is the proportion of some rainfall. For example, let us say rainfall is 10 millimeter, runoff may be, let us say, 5 millimeter only. It means 50% rainfall is where it has gone. It has gone to all these processes. So we have to calculate each process. Finally, we can calculate what is the runoff in the river. If runoff is very high, it will convert into the flood. So today I will show you two types of models which will show you simple flow as well as the flood flow. So what is the basis of hydrological modeling? This is the main basis of hydrological modeling. As I told you, input is the rainfall and our main target or outflow is the stream flow. So I will start from precipitation and finally stream flow. In between there are different processes. If you make a water budget, it will be like that. Input minus output is equal to change in storage. Here input is the precipitation, output is the stream flow, and total storage change is this much. So if we can note down this equation like that, precipitation and incoming of groundwater from other aquifer minus evaporation, transpiration, irrigation if there is any additional irrigation, outflow of the groundwater and the stream flow is equal to the change in storage. So this is the basis of any hydrological model. Now there are different type of hydrological models. You must have heard about empirical models, physical based model, conceptual model. So what is the empirical model or black box model? They are nothing, simply they are black box. As a scientist, I may know many things, but as a user, I may not be interested in all these processes. I wanted to know, suppose today 100 millimeter rainfall occurs, how much flow will be there in Ganga river at Haridwar? This is my target. So I am not interested in what is the process. So it may be, for example, 10 millimeter rainfall. If after this calculation I found a relationship that runoff is equal to C1 into rainfall. C1 is, let us say, 0.6. So 10 millimeter is there, it is a 6 millimeter of runoff. So what is this 0.4? This is, so this transfer C1 is, the 0.4 is the transfer function. It's a purely black box. So there are many models. In fact, for all river-based country, these empirical models, black box models are available, and generally quickly engineers estimate that. For Ganga basin also, there are some models are available, like runoff is equal to rainfall, C1 into rainfall plus C2. This is one model. They are the black box. They are based on the experiments. 30 years experiment, 40 years experiment. We estimate and finally we get some model. Second model is physical based model. Physical based model, basically each estimate the each process. So known physical laws of various processes are used to model the catchment response. Okay, so this is the physical based model. I have a physical basis of each equation. It's a very complex model, highly data driven. In fact, simply if you estimate the interception, you should know land use land cover, that leaf area index, then there are type of the leaf. It's a highly, so for one estimating one parameter, evapotranspiration, around 40 parameters you need. So for entire hydrological modeling you need maybe 100 parameters. Hence they are quite complex, but they are very accurate. While empirical model are case based. So engineers or scientists, they are neither interested in this black box model nor interested in physical based. They compromise between this. So that is known as conceptual model. Conceptual is somewhere wherever it is required is empirical, somewhere wherever it is required is physical. As I given the one example, interception. So in entire hydrological modeling, let us say evapotranspiration, estimate using the physical based model, but interception by thumb rule. Thumb rule may be like forest, if it is a dense forest, 20% of rainfall is interception. If it is a agriculture area, then 5% rainfall is the interception. So some part is black box, some part is physical based. So if you combine these two things, it becomes conceptual hydrological model. So different modeling approach, empirical, physical based. There may be event based. Event based means like suppose there is a rainfall, one event of rainfall is there, one continuous today, 1 hour, 10 to 11 rainfall occurs. What is the runoff? That is event based. Even in a one day, this much rainfall occurs. What is the runoff? This is the event based. Continuous means every minute, every half an hour, every 1 hour, every day you estimate. So this is the continuous simulation. You can use empirical, you can use physical based. Now, there is a definition of models like lumped model, semi-distributed model, fully distributed model. Let us see what is these models. If you see the figure on the screen, the first figure, left side, basically there is an entire hydrological process, and in a watershed or in a basin you will find, suppose maybe land use is different here, land use is different here, land use is different here. Soil is different here, soil is different here, soil is different here. It means land cover is different here, LI will be different here, soil means infiltration will be different all the place. But in lumped model, I consider only one parameter. So there is no heterogeneity. I consider one unit as a homogeneous unit, which may be a basin or sub-basin. So this is known as the lumped model. For example, I use for peak rainfall runoff, I use Q equal to CIA, and I consider that C value, constant C value in entire this area, then it becomes a lumped model. This is a very accuracy is not good. In semi-distributed model, what we do? We consider one unit and we lump the entire model into one unit. Like it may be a sub-watershed, it may be a HRU, hydrological response unit, it may be plains, hill plains. So one unit I will consider as a single unit and lump the model, then I will route my model to the outlet. So this is a semi-distributed model. The third model is fully distributed. So I consider heterogeneity of entire grid. In all, when I divide entire watershed or basin into grid, small grid, each grid will have value. Then I will consider calculate water balance or runoff at each step, each grid. Then I will route that model to the outlet. So every point is considered in this model. Finally, you will get the runoff at the outlet. So if you have a physical based model, if you have a fully distributed model, it will give you a highly accurate information of the runoff at the outlet. That's what I want. So distributed model take a explicit account of spatial variable of processes, input, boundary condition, and system characteristics. In our case, it is a watershed or basin or sub-basin. But then question arises and many people ask which model is suitable. So there are certain criteria for it. For example, you should see the space discretization, hydrological process, vegetation layers and soil layers. Out of that, first two are very important. So space discretization means if you are using lump, I consider it as a low rank model. If it is a semi-distributed, moderate rank model, if it is a fully distributed, grid-based, highly ranked model. In hydrological process, empirical approach, not consider or low rank, conceptual approach, moderate, and physical approach, high. So if I consider these two criteria, then if I say distributed and physical approach, this model is the most suitable for me. Of course, there are some more like vegetation layers also you can look, single layer, two layer, multiple layer. Generally, in snow melt modeling, we are looking into these models. And soil layers like maybe conceptual model or finite difference and finite element discretization of the soils below ground soil surface. Soil surface as well as the XYZ direction of the soil. So that's how we select the model. So some example, HEC-HMS, SWAT, HEC-HMS, HEC stands for Hydrologic Engineering Center, HMS stands for Hydrological Modeling System. SWAT, Soil and Water Assessment Tool. HEC, this is again European Hydrological Modeling System. SHE, HEC is a company name. SHE is basically some system, Hydro, Europe, or it is basically hydrological modeling of the, then finally with variable infiltration capacity model. So if you compare these four models, so what are the advantages? Focus on a runoff channel, for example, HEC-HMS. Okay, out of these four models, three are free. HEC-HMS you can download from the net. SWAT you can download from the net. WIC you can download from the net. And you can start working on it. HEC you have to pay a lot of money. So that you should consider. Suppose you are looking for only free, so then you can remove this HEC, you will have three. Out of three, suppose you are looking for you are mainly interested in physical based. So you can see HEC-HMS empirical, SWAT empirical and physical, then WIC physical and physical. So again out of three you choose, okay, I am interested in physical and physical, so let us go to WIC model. So that's how we choose the model. And finally, different outputs and all these things we decide. But it doesn't mean that HEC-HMS is also very good. It is not necessarily always you should be 100% correct. Even if you are 80% correct, your job is done. So sometimes even WIC is much better than HEC-HMS, sometimes HEC-HMS is also very good. I have some example. So now what are the steps in hydrological modeling? First, delineate your watershed, delineate your catchment, delineate the basin. Okay, now question arises, what is watershed, what is catchment, what is the river basin, what is the sub-basin? Technically speaking, practically, all are same. The definition of watershed, catchment, river basin, basin is same. A watershed is a drainage area from which runoff flows past to a single outlet. The definition of watershed, same is the definition of basin. Basin is an area or drainage area from which runoff flows past to a single outlet. So what's the difference? Difference is only the size. Generally, when we are talking about few hectares area, it is a micro watershed. Few square kilometer, sub watershed. 100 square kilometer or maybe 200 square kilometer watershed, maybe 1000 square kilometer sub-basin, maybe 10,000 square kilometer, 50,000 square kilometer we call basin. For example, Ganga is a basin, Yamuna is a basin, Parvati may be sub-basin of Yamuna. But if it is a small area, maybe Swan river, so we call a Swan watershed. Maybe in your area you find some small area, you call a watershed. By definition it is same. So first step is delineate the watershed. Second step is obtain the hydrological and geographic data. I will touch upon it a little later. So all hydrological information you should get now. Geographical information you should get now. Third one is select the appropriate model. What is the modeling approach you want? Fourth one is calibrate and verify your model. And fifth one is the use for assessment, prediction and design. So these are the 5 steps. So now let us start with first one, how to delineate a watershed. To delineate a watershed, there are two things. Either you should have a contour map, you can delineate the watershed. But nowadays, in the form of GIS, in our once you have a GIS, then if you have a DM, very quickly you can delineate the watershed. So, first of all, how to create the digital elevation model? If you have a contour map in GIS environment, you can interpret it, you can get a DA. Or let us say in ArcGIS, you can make a tin and you will have a DA. But remote sensing will also help you to get the DA. There are different techniques. One is that if you have optical data like CATCHMENT, ESTER, you can generate the digital elevation model by using a stereo pair. If you have a SAR data, microwave data, synthetic aperture radar data, then generate the interferogram and you will get the SAR interferometry, and using SAR interferometry, you will get the digital elevation model. Third one is the LiDAR. So if you have a LiDAR data, you will have elevations, so you can have a DA. So these are the 3 techniques. So remote sensing can be utilized. Now, some data, free DMs are available. For entire India, Kato DM is available. That is the example of first one, stereo pair. ESTER DM is available. Then you have a SRTM DM, that is the example of second DM, SAR interferometry. So these are the DM which is freely available, you can download. So now this is one example, you can see a watershed. This is a contour map, this is the outlet, and you can look into the ridge line and you can get a contour map. Now if you have a ArcGIS, make the tin and you will get the digital elevation model. Okay. Otherwise, directly you can take DM from either CATCHMENT or ESTER or SRTM. So this is the example of, this is the tin of area. This area is basically a watershed known as Pali watershed, is the backside of the Mussoorie, which is again a part of Aglar watershed, which is a part of Yamuna basin. So this is a Pali watershed and you can see the tin of it. Now after that, so this is one parameter, topographic parameter. We will start one by one. So we have this watershed DM. So I can have a nice gridded DM from it. Then next step is I can have a slope map. Now this I have used, either you can use ArcView or you can use ArcGIS. So there is an option in ArcGIS, ArcHydro. You can go and you can calculate all these things. So you will get the slope map of your watershed. This is also required for hydrological modeling. Why it is required? Because water follows the slope. Water moves from high point to low point. So DEM and slope is necessary with the flow. The next step is we calculate the flow direction or aspect. What is the aspect or flow direction? How water will move from the north direction, south direction, east direction. So we calculate using this model. Then next step is, so this is the direction, like 1, 2, 4, computer understand 0 and 1, so bit system. So for computer, in our mathematics, we have, base 10, like 1, 10, 100 is a base 10, while for computer, base is 2. So 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 it is 8, 2 to the power 4 is 60. So basically base is 2 for computer system. Hence, when I say 1, it is basically 2 to the power 0. So it decides the direction. So I say, okay, it may be like 2 to the power 0, it may be east. So 2 to the power 2, 2 to the power 1 is the southeast, 2 to the power 2 is the south. Like that I decide. So 1, 2, 4 are the nothing, simply a number and tells about the flow direction. Once it is done, the next step is to estimate the flow accumulation. So you can see now, flow accumulation means at particular grid, how many grids are coming, contributing to this. So we calculate, and once we do this with some threshold, there is a small wonder. The moment we do this, we suddenly found before us a drainage network. So automatically you get a drainage network using the digital elevation model. Now you see, these are the steps, one by one. I started with the digital elevation model. I convert it, then I calculate the slope, then flow direction, then flow accumulation, and I got the drainage network. This is the, if you don't have a drainage network, if you don't want to digitize the drainage network of your area, no need to worry. Use the GIS, use HEC-Hydro or any other GIS. In ILVIS also it is available. ILVIS again I will tell you is the free software available on the net. So you will get the even a drainage network of that area. And it will tell me how, so the moment I will get a small area and I will get the watershed. So like that I got a watershed. So that's how I delineate the watershed. The next step is, once I decide the watershed, then all these parameters, next step is, I should know what type of the soil. Not only the type of the soil, I should know that the property of the soil. So property of the soils are hydraulic conductivity, infiltration rate, texture of the soil, bulk density. All these parameters should be defined. It will be a part of the model, because infiltration rate will give you how much water is percolated. For example, suppose rainfall intensity is 5 millimeter per hour. Infiltration rate of your soil is 1 millimeter per hour. It means where remaining water is going, it will decide, okay, 1 millimeter per hour it is going to the ground, then remaining water is flowing over the land. It will become over land flow. So this infiltration rate of soil or hydraulic conductivity is very important. Hydraulic conductivity, why it is required? Because in the subsurface flow, water flows the law of Darcy's law, which is nothing based on the hydraulic gradient. So Darcy's law says velocity of the flow in the soil is equal to K into I. K is the hydraulic conductivity and I is the hydraulic gradient. So for that also conductivity is required. So you can calculate subsurface flow, even for groundwater flow also hydraulic conductivity is required. So all these parameters are required and you have to incorporate into your model. Then second one is the vegetation. What type of vegetation? Because vegetation is important. Vegetation will tell you how much interception takes place. Good vegetation, high interception. Poor vegetation, low interception. Not only that, it will tell you the transpiration. Good forest will have high transpiration or evapotranspiration. Poor area, poor forest, low evapotranspiration. Bare soil, evaporation takes place. So land cover, land cover of vegetation is very important. And so what are the parameters for this? Parameters for this are albedo, leaf area index, and all these parameters, land cover, all these parameters I am getting plant height from the remote sensing data. Next step is, get the meteorological parameter, because how much water is coming to the ground depends on the rainfall. So precipitation, temperature, relative humidity, wind speed, and this generally we get from the any weather station. Some information nowadays is available from from satellite also. So you get the precipitation. Once you get the precipitation, then put in the model. Temperature, relative humidity, wind speed is required for evapotranspiration. Precipitation is required as an input, so that I should know how much will be the runoff. So if suppose in your area you are having 6-7 stations, some rain gauge stations to interpret. There are different interpolation techniques. Generally people are using, or engineers are recommending, if it is a plain area, Thesian polygon. If it is a hilly area, then iso-arterial techniques. So nowadays GIS provides such tools, directly you will get a Thesian polygon. Or you can use IDW also. So these are the parameters required. Then you have to calibrate the model. So what is the calibrate the model? So what is the calibration? Calibration is defined as the model parameter and variable adjusted to force model output to match observation. Purpose to obtain an economical and reproductive method of identifying a parameter set to give the best fit between observed and simulated value over the calibrated period. It will little bit later it will be clear. Why calibration? Uncertainty in model input. Models simplify the complex process scale versus catchment scale. Then what is validation? Validation simply you verify. Validation is a procedure to ensure that all components of the model give an accurate reflection of the model's conceptualization. In a validation model, each component requires individual validation. Validation includes that all the theories and assumptions are correct. Then sensitivity analysis, again, how sensitive is your parameter? So sensitivity analysis builds confidence level in the model. Sensitivity is measure of fact of change of one factor on another factor. Why sensitivity analysis? Better understanding of the model. Real world. Keep model simple. Identify significant and insignificant. In the model, there are some insignificant parameter. There are some significant parameter. So you will understand that how significant is my individual parameter. Some parameter you can avoid. Identify interaction of the model component to parameter. Identify the stability of the results. So these are the steps of modeling and validation and sensitivity analysis. Now, why remote sensing? Because it gives the near real-time hydrological information, it gives the temporal information, it gives the spatial information, it provides synoptic coverage, it non-interference with observation site, and it is a digital information directly incorporated in any GIS system or hydrological models. Okay. So far I have discussed in detail about the hydrological process. Then what are the steps? Now with the case study let us start how actually hydrological model works. So this is almost live example, but I put in the slides only. So this is one model, SWAT model, soil and water assessment tool. It assesses the water like runoff, it assesses the soil like soil erosion. So this is the model. Now nowadays it is available on ARC platform also. You can have a ARC SWAT or you can have a ARC Blue SWAT. It's up to you. Now how it works? So now what is the how it works? So it needs some input parameter. Already I have discussed. The first and foremost input parameter is digital elevation model. So you can see you should have a digital elevation. Then you should have a drainage network. You should have a land use line cover. You should have a, some tabular data like bulk density, hydraulic conductivity, LAI, albedo. You should have soil map, soil, so all these parameters you should have, and you should have a better information. Then it creates the HRE based on the land use and soil. Then it forces the model to from the precipitation point of view and temperature. Finally, it will give the, so you have to parameterize it. It create the database, parameterize it. Then once you get the output, Let us say your runoff, then you calibrate. So now question arises, what is calibration? So you find out that yes, my output says there is a runoff of 20 cubic, but it is coming only 10 cubic. So what is the problem? So now I have to look back into the parameter which I have. I found by mistake the curve number which I have given is wrong. For forest, I am giving curve number 70, while for forest it is 30. So I have to change it. Once I change it, I will calculate. I found now it has improved. Actually it is 20 cubic, now it becomes 80. So I can say now I improved by calibration. So this is calibration, and validation is the matching between the observed and the estimated. So now it is clear that how calibration is done. So you will get the output. Now one by one we will start. So okay, some definitions are there, like what is SWAT? A evaluation of watershed scale model. It is a physically based. It is some part is empirical also. It is computationally efficient, enable area to study long-term impact. SWAT is a continuous time model. A long-term model, the model is not designed to simulate single event, but basically it is for, or not for flood also. It is a combination of various models which were developed earlier. So, water balance is the heart of the model. So, hydrology like canopy storage, all the hydrology is involved here. Whatever I have discussed, infiltration, redistribution, evapotranspiration, subsurface flow, surface runoff, peak runoff rate also, ponds storage, then transmission losses, all these, this is the hydrology. And it estimates it route the flow, so that at the end you will get it. So we will consider only flow routing and flood routing. So the procedure. So now one by one, first is load or select the SWAT extension. It may be AB SWAT 2000 or maybe new one also. Now you have AB 2010 also. Delineate the watershed and define the HRE. Delineate the watershed and define the HRE. Edit SWAT database. Define the weather data. Apply the default input file writer. Edit the default input file. I will come back to it. Setup. Required specification of simulation period. PT calculation methods. Run the SWAT. Apply calibration. Analyze, plot, and get the output. So these are the procedures. If you recollect my last 40 minutes lecture, I have spoken to each and every point. Now let us see how it works. So this is the area, this is the UMIAM catchment. It is, if you go from Guwahati to Shillong, in between you will find this UMIAM catchment. And this is the UMIAM lake, and this is the catchment. Now, so this is a UMIAM catchment FCC. You can see different, this is the UMIAM lake. And this is the entire catchment. You can see good forest also, you can see settlement, you can see the June cultivation area also, bare area also, all these things are available. Now next step is, I have to define the path where my data is available. So you have to define the path. Create your project and define the path. All the database wherever your data is available. Next step is, start which is available in your database. Next step is, you see your DM, whether you, generally digital elevation model is already projected model, some projection system is there. At this moment you have a flexibility, if you want to change the projection, here you can change the projection system also. If not, then you use the same. So then next option is, it will ask you any warning option. So you tell, yes, drainage, if you have a drainage map, you put as a hard line so that it will follow the path. If it is not there, automatically it will calculate, you need not to worry. Next step is, okay, you can change the projection here. Then you can get the mask, if any mask is there, like watershed boundary. Then you put all the value and run. So it will calculate and it will tell you, and not only this entire watershed, it will tell you it will give you the drainage network of that watershed. Now you have to define the outlet. For example, this is the main outlet. Maybe sub, you have to tell, okay, you want sub watershed. So you can put all these dots. This option is available. So it will calculate hydrology based on the sub watershed device. So you can see it calculated the sub basins. You can see all the sub basins here in your screen. Okay. Next step is, now you have given the digital elevation model, you have estimated all the parameters required, it is there. So you cannot see, but inbuilt automatically it will store in its database. Next step is, it will ask you the land use information, it will ask you the soil information. So this is you can go to the menu and then you will have a land use and the soil. So now you can browse where is your land use map, where is your soil map. Next step is, you can browse. Remember one thing, in these models, for each area, each type, there are some, nomenclature. For example, agriculture, it will not, agriculture at AGRICULTURE. It has some name there. So you tell, agriculture means this name, forest means this name. Then only it will understand. So this is small modification you have to do. Once it is done, so your model is ready. This is for, let us say, soil map. Then all these things are available, so it will calculate what is the percentage of soil, different type of soil, different type of land use. Now next step is weather data. So HRU, you go HRU simulation, it will estimate the HRU. Once it is done, it will derive the HRU, then it will ask for the weather data. So you have to give all your weather information, like rain gauge, position of the rain gauge, then some Excel table is there for the rainfall data, you can provide that table here. Similarly, other parameter it will ask. So you can give by default also, otherwise if you have the data, you can give it. So now, digital elevation model, land use land cover, soil and weather. So now you have incorporated all the parameters. Finally, you have to run. So simulation, you come to the simulation, it will ask from which date you want to start your simulation. January 1st, some year you get it, to December 31st, let us say for 1 year. Then again it will ask what discharge you want. You want daily or monthly or hourly, that will decide. It will also ask you the evapotranspiration technique. It has many evapotranspiration technique. You can choose anyone. However, you can go for Penman Monty, which is very good. Once it is done, you can simulate and finally you will get. So this is the different, one by one it will ask and you can give the answer. Finally, it will calculate the. So you have to go by chart. You can choose the option, it will prepare the chart. Now what chart you can see, right side you can see is sub-basin map of your watershed. Then you have a table and the chart. It will give you every day what is the runoff of your area. For example, this is a basin, so you click on this basin, you will get the chart. You click on some other basin, you will get the chart. You click on some other basin, you will get the chart. So this is in nutshell a case study of hydrological modeling using the SWAT model. Similarly, there are many other models like MIC, BIC, HEC-GeoRAS. You can use those models. They are very simple, user-friendly, except BIC. BIC is quite complex, but other models are very simple. They are window-based, you can directly use, but procedure is same. Everywhere you have to give digital elevation model, everywhere you have to provide land use information, everywhere you have to give soil, everywhere you have to give weather information. Then you have to choose which procedure you want to use. The moment you will complete it, run the simulation, you will get the answer. This is the information we have derived for simple flow. But now let us go. If there is a heavy flow, then what is the flood situation? So if it is a heavy flow, then it will not be we call it a flood modeling. In place of hydrological modeling, now it is a hydrological modeling, but we call it flood modeling. So I will now discuss about that. So flood inundation modeling. HEC-GeoRAS and HEC-RAS for flood simulation and flood mapping. So HEC-GeoRAS is basically a GIS window version, graphic user interface of HEC-RAS only. Some simple GIS operation you can do here, import the data to HEC-RAS model, and finally you will get out. Now, with the help of a state case study, let us try to understand this. So, means HEC-HMS is basically for hydrological modeling, but then you have to route the model so that you will get the flood waves. For that you need HEC-RAS. So HEC-RAS is basically, earlier it was known as HEC2, nowadays it is known as HEC-RAS, and GOI is HEC-GeoRAS. Now how it works? So like you have a all database, then go to HEC-HMS for flood discharge, but then it will give the point information. Finally you have to route in HEC-RAS, and you will get, you can generate a scenario like this. So first step. So this is one example. This is the Daya river in Odisha. So I will model now this for flood. So I need some information like Manning coefficient. So Manning coefficient means nothing but roughness coefficient. How rough is your surface? Roughness is high, it means runoff is less. Roughness is low, runoff is high. Because velocity is equal to 1 by n r to the power 2 by 3 s to the power 1 by 2. So 1 by n is the Manning coefficient. So roughness is high means 1 by n. So velocity is low. So discharge will be low. That's how it works. So you can see different runoff coefficients. So for this you need land cover, land use. So the process is started like that. You get a FCC, you get a digital elevation model, then you got what you call, now you start working on stream center line, river. I will show you flow path, all these things. Then RSGIS import file to HEC-RAS, adjust cross section, completion of geometric data, flow simulation, and then inundated data. So how it is done? So this is you have to go to the field to see the cross section. These are the cross section as well as the stage information. Stage discharge relationship. Stage discharge relationship known as the depth of the stage means depth of the water in the river, and discharge with respect to discharge. If depth is, let us say, x meter, so what is the discharge? So this is two things, rating curve as well as the cross section of each point we have collected. Now first thing, create stream central line. So in FCC you can see a river, so create the stream central line. So how to create the stream central line? You can see here. Now first create the river bank. So both the river is visible, so you can digitize the line, a segment along the river. It will be like that. Now create the flow path. So now you define the flow path. So entire river cross section is the flow path. Third one is create the cross section lines. So now you put the cut lines, these are the cross sections. Then create storage area. You know that once flood comes, so flood means as I told you yesterday, your water level will cross the river bank. And what happens? First it simply rush to the low-lying area, and that area is the storage area. So you have to, so if you have a DEM, if you have a, then you can really define in the GIS what is your storage area. Then next is the create the n Manning coefficient n value, which is a function of land use land cover. Already I have shown you. So you define now the same values here. Then if you have a DEM, already it is there, you put it, otherwise you can create now also 10 from the DEM. Then complete your center line, you complete everything. Center line elevation you define, now check and define. Cross section, elevations and different cross section like what is the width, or what is the top width, what is the bottom width, what is the length, what is the slope, all these things you have to give. Then Manning's n value complete, storage area complete. Once it is complete, then import to the HEC-RAS. Now, so you import the geometric data to HEC-RAS. So all informations now are available on HEC-RAS. Then you start working on correcting your cross section. Sometimes using the DEM, you find very absurd cross section. For example, in one area, actually river is flowing like this, bottom is like this, but it is showing like this. You correct it manually, so it will become like this. So now what will happen? Water will flow here, it will not cross this. So that's how you improve it. So we improve like this. So cross section from survey data, okay, this is all. So that's how we are improving. So input flow data, stage data, then run the hydrological simulation. So you can now here define which date to which you have to run. Once you have run this model, the next step is you will get the flow. I am sure that you must be seeing animation. This animation show you along the river or a particular cross section how water is going up with respect to time. Time, it is a 6 hourly, that let us say 6 p.m., 12 midnight, 6 a.m., 12 afternoon, like that it will calculate. You can run the model for hourly basis also. Basically in flood simulation, we run the model on hourly basis. So then now next step is, as I told you yesterday, that I am not interested in all these depth, whatever you are seeing as a user. I am interested, I wanted to know whether my house, when water is coming to my house, when water is coming to the road which is close to me, so that I can evacuate it. For that, now you bring FCC and DEM and apply this depth. So there is a separate, post-RAS setup is there. You run that, it will ask the all the GIS data. Then it will ask the DEM. Then it will calculate the flood. It will delineate the flood area. Now you can see through animation. So you can see here now that how this is the FCC, and you can see that after calculation along the river or a cross section, how water is going up with respect to time. Simultaneously, it will show you that this water is moving, at what time this water is moving here. For example, let us say your house is here. Now you know at what time this is changed. So maybe in next 6 hours only your house is inundated. Suppose your house is here, you need not to worry, water is not coming there. So that's how we do the hydrological modeling or flood modeling. So this is all for today. I have completed this. Thank you very much.